Okay, so hopefully everyone can see the presentation here. We usually like to start out our e-learning seminars by reminding anyone that's seen any of these previously, or telling you if this is your first e-learning seminar, that we have a new website format at CAEI.com that we're very proud of. We have expanded our resource library. That resource library includes links to the e-learning seminars that we've already conducted, recordings of those, which you can watch at your leisure, as well as other information that we've placed for public consumption, things like our update seminar notes for the new releases of Ansys that we provide every year. They're fairly detailed. The update seminars are usually an all-day-long presentation consisting of Workbench, mechanical APDL updates, additional products like the Ansys Composite Prep Post, EKM, some high-performance computing, as well as what's new in the world of Ansys CFD. So if you're interested in seeing any of those notes, if you were unable to attend the live seminar, you can download a PDF copy of those notes to review what is new and exciting at the new release of Ansys. We've streamlined our training registration and calendar view. You'll find that it's much easier to find the classes and register for them right there on the website. And also, we have a new Engineering Advantage blog, which we've been trying to add to at a fairly regular basis, and we would encourage you to take a look at the blog. It's basically the entire staff here at CAEA taking turns basically giving their impressions and opinions on certain techniques and capabilities that pertain not just to Ansys, but also to general finite element analysis. So you might find there's some useful topics in there. But we would encourage you to take a look at those, and feel free to comment. If you like the blog, let us know, and we'll continue to provide them. So this e-learning webinar is part of a continuing series that we've been doing at CAE Associates, where we pick a particular topic, in this case assembling models in Ansys, and we try to cover them with a brief demonstration over about a 30-minute period. So they're quick, they're concise, they're very topic-oriented. If you have attended these in the past, you'd know that you can go to either our website or another new addition linked into the website is our YouTube channel. So if you have trouble viewing either on YouTube or on the website, you can try one of these options to look at previously recorded e-learning seminars. So we try to record all these seminars as we're doing today and put them online so that they're available for people to either look at again or review, see if there's any interesting topics that they may have missed or were not available when the original presentation was conducted. Also, if you are a New Jersey or New York resident and you're looking to earn continuing education credits for attending the full presentation, all we ask is that you complete a survey at the conclusion of the presentation, which will be emailed to you. So on to the subject at hand. We're going to talk today about assembling models in Workbench version 15. That is the current release. And with version 15, we now have two different ways that we can assemble previous finite element models inside the Workbench environment. The first is to use the external model utility, and this is a new function at version 15. And this allows us to take meshes that were generated in mechanical APDL, or what we used to refer to as classic Ansys, and bring them into the Workbench environment. We'll be demonstrating how to do that today. And then secondly, we'll touch again on using the Act Assembly Manager for assembling separate Workbench models. So we're really looking at this from two different directions. One is you may have a bunch of legacy models that were created in mechanical APDL. All you have are a finite element mesh of elements and nodes, and you'd like to somehow bring those into the Workbench environment and additionally assemble them with other existing models. And that's what the external model utility will allow us to do today. So let's get right into that. I'm going to switch over now to, let's go back to mechanical APDL. So the first step in bringing one of these models into the Workbench environment, again, this would be a legacy type model, a legacy mesh that you got into either created in mechanical APDL or may have imported from another mesh generation tool. So we have could potentially have solid model geometry in addition to the volumes, in addition to the elements. In this case, we don't. If I were to do, say, a volume list here, we'll see there are no volumes available. All I have are nodes and elements making up this mesh. But that's okay, because if you're familiar with how the interaction between mechanical APDL and the Workbench environment occurs, there is no geometry sharing directly between them. The only way to really get geometry from mechanical APDL into Workbench is to write out an IGES file, read that into Workbench, but then you need to completely remesh that part inside the Workbench environment. So what we're going to do here now is take this finite element mesh, these nodes and elements, and show you how you can bring them directly into the Workbench environment. And in the process, Workbench will develop a pseudo-geometry based on the finite element mesh facets, and we'll see how that's done. So step one, you have your mesh in Mechanical APDL. You go to the General Preprocessor, or Prep 7, and come down to the Archive Model menu and click on the Write option. And this is the CD write command inside Mechanical APDL. Now, the file format that's going to be read by Workbench has to be in a CDB format, so it has to be written out of Ansys Prep 7 in order to use this utility. When you're writing out the information, you can use the DB file type, or database file type, which is basically all finite element information, because all we're interested in getting at this point are the nodes and the elements from Mechanical APDL. So this file gets written out, and then we would switch over to the Workbench environment, and you'll find under the component systems there is now this utility external model. It's right below the external data. And it actually works very similar to external data if you've had an opportunity to use that in the past. You drag it, you drop it onto the page. Zoom in on my plot here. Double click to open up the utility. And you'll see it's asking you to provide a file that you're going to import into Workbench. So we browse to a file. In this case, we'll start with the rotor. I have a finite element mesh of the rotor, and we're going to add to that a mesh of the blade that we were just looking at. So we start out by looking at the details of this particular CDB file. We want to check and make sure that the length unit is consistent. And if we need to do any kind of transformations from one coordinate system to another, we can do that using these options down here on the right. In this case, the rotor is going to be our base geometry or our base model. So we're going to bring that in and assume that it is aligned with the global Cartesian coordinate system in which it was modeled in Mechanical APDL. So I'm going to click again to add a second file because we can create an assembly of these mesh files, all using this one same utility. And we're going to go for the blade in this case. And once again, we're going to bring it in with respect to its original orientation. In future, what we can do is also copy that blade. In fact, let's do that now. Let's add in another copy of this same blade element model. And I can insert a transformation. So I happen to know that these two blades are offset by 10 degrees in the original assembly. So I can come down to my theta xy block here and put in a value that represents that 10 degrees. Notice that the units are in radians. There's no way to currently change that with the utility at this point. So I'll put in a value for 10 degrees in radians. And now we'll return to our project page. And it's going to ask us to basically update or read those files into the external model. So we get our check mark, we're ready to go. The next step now is to get this into the mechanical environment. So we're going to go over here, grab one of our analysis systems. We'll just take a simple static structural at this point. And notice I have a couple of options for where I can drop it on the page, but none of those options occur dropping it on external model. Okay? It needs to be dropped in as a standalone system on the project page. Once that's in place, we're going to then take the setup bar from the external model, and we're going to drop it on the only place that we can, which is the model row of our static structural. Now, before I do this, watch what happens to my geometry row in static structural. Notice that it disappears. It gets condensed out. Because we're using this external model utility, the analysis environment knows that we're going to interpret or create a pseudo-geometry from the finite element mesh. Now, if I click on my model row and I turn on my properties menu, I can see over here that I have another unit. I want to make sure it's consistent. And I have a tolerance angle, and I have an option to process nodal components. If you're familiar with FE Modeler, the FE Modeler utility, this is really an abbreviated version of the FE Modeler tool. They've basically taken out the user interaction that had to occur with FE Modeler and condensed it all into a simple drag and drop operation using an external model. So to view this geometry, we're going to right-click and open up Mechanical. And what's happening now in the background is that, as I mentioned before, these mesh files are now being read into FE Modeler in the background. FE Modeler, if you're familiar with its terminology, is creating skin components from the finite element facets. And then from those skin components, it is constructing a geometry that we will have available to us in the mechanical environment. And that's an important thing to keep in mind. when we bring a model into Ansys Mechanical inside Workbench, we have to have some geometry behind that mesh. Since we started with a static mesh in Mechanical APDL, something in that process had to create this geometry for us, and that is what's occurring right now with FE Modeler in the background. So we allow it to do its thing, and we'll notice that we get our part now in the mechanical environment. And again, this is an assembly. This was blade number 1. This was blade number 2, offset by 10 degrees. And this was my rotor mesh that I brought in. If I want to view that mesh, I can simply click on Mesh, and there it is. It should look exactly the same as the exported mesh because it's simply using those nodal coordinates and connecting them together with elements. But some of the subtle differences that you'll see between the original mesh file and now the Workbench version of this. If we open up geometry, as I mentioned, we'll have actual geometry, volumes made up of surfaces, made up of edges, made up of key points. But one thing that's kind of interesting here, normally you would expect to see, in terms of line segments, multiple surfaces, say on the curved surface here. You may see a division of the rotor at the end of the fillet radii. We don't actually have that here. If we click on the surfaces that were constructed from the finite element mesh, let's turn on the mesh to show that, you can see that we have one continuous surface along that face. Because again, what it's doing is using a fairly liberal concatenation tolerance to take the surfaces from the finite element faces and construct from it one large surface in this case. So you can edit that value. If you recall back on the project page under those properties, you can loosen that tolerance up a little bit, but what you're going to find is that you're going to be getting a lot of smaller surfaces that are going to start to look more and more like the actual mesh. So it depends on the amount of resolution that you need in the geometry in terms of the boundary conditions that you are applying for you to choose a particular tolerance angle. I'll give you another example. Up across the top here, if I pick on, let's turn off my mesh, and if I pick on the surface on the top of the rotor, notice that has also been concatenated into one single surface. And again, that's because by default we're using a fairly liberal tolerance angle in the external model utility. A couple other things to note. We have one body that represents the solid rotor. We have 2 parts, essentially, that represent the blades. So in part number 1, we have 3 different bodies that make up that blade. Now, why did that occur? How was Ansys Workbench smart enough to recognize that they were separate bodies? Well, very simply, if we jump back to the Mechanical APDL mesh, we'll see that there are several different types of element types that are being used here. We're doing a hexatet transition from bricks on the blade section, bricks on the base, and then tetrahedrals and pyramids in the center. So that's enough for Ansys to realize, okay, these need to be separate bodies because they are actually separate element types in the original mesh. So that's where that comes from on the mechanical side. Now, one thing to be aware of, no material properties are brought across when you read from FE Modeler. So everything's going to be defined as its default structural steel or whatever default material you happen to be set up within mechanical. So you'll have to go back and basically pick on your volumes and reassign the appropriate materials to them. If we look at connections, because we have geometry that we can pick on that was constructed from that mesh, we can create automatic contact connections. So let's connect the blade to the rotor. I'm going to go in and insert a connection group. In that connection group, I'm going to include 3 bodies. And then I right-click and say Create Automatic Connections. And I end up with 2 contact regions between blade 1 and the surface, and then between blade 2 and the surface. And these contact regions can be edited. They can be changed, added to, deleted, anything you want to do, like a standard contact interface that you would create with a normal Workbench model. So really no difference there at all. When we get to the mesh, we'll notice that there's not a lot available in the details for the mesh. The mesh statistics are still there, so if you wanted to look at a mesh metrics for, say, aspect ratio or element quality, they are all still there. They work the same way. But there's no ability for me to either clear or recreate the mesh. In fact, if I go up to the mesh pull-down menu under mesh controls, you'll see that they're all grayed out. So the meshing capability is disabled when we bring a model in through the external model utility. We're assuming that the mesh that was created at the Mechanical APDL level is the mesh that we're going to use in Mechanical. Now, if you needed to change that for any particular reason, you can always go back to mechanical APDL, make your alteration, and just simply refresh the external data utility and refresh mechanical. And that will bring the new mesh in into the current model. Other than that, things are pretty similar. Like I said, if we wanted to do some things like put some frictionless supports on these surfaces, we pick on those surfaces. Right over to environment, fixed support or frictionless support. Everything is set up pretty much the same way we would operate with a normal mechanical model. I just want to point out a few other things about this particular utility before we move on. What we'll do at the end of the presentation is open up the lines. We'll use the chat window and open up the lines if there's any questions. So keep those questions in mind, make a note, and we'll try to address them at the conclusion of the presentation. So a couple other things to keep in mind. What you get an imported mesh, you get mesh metrics, and you get geometry that you can use, as we just illustrated on the mechanical side. What you won't get with the utility are the materials, the original materials assigned to that mesh. Those need to be reassigned. If you used a symmetry boundary condition, or if you had any contact or elements that were in the original mesh, those will also not come across the interface. Those will have to be recreated when you bring the mesh into mechanical. And again, they've disabled any of the meshing capabilities. The assumption is that you're utilizing the mesh that you're importing from the original CDB file. This works for solid and shell elements and also mixed assemblies of solids and shells. Be aware that the node numbers are reordered. There is an option inside FE Modeler to suppress nodal reordering. So if you are using particular node numbers for different boundary conditions or things like that, you may not want to use this utility. You might want to use the full FE Modeler interface and instruct it not to reorder the node numbers. Important, no line elements of any kind are supported. So no beams or spars or anything else will be recognized by FE Modeler. That is just a limitation of the FE Modeler utility. And you'll find that any legacy element types that you're using, things like solid 42s or solid 95s, solid 45s, they're going to be converted to current technology elements when they are read into the Workbench environment. So your tetrahedra will be converted to 187s, your bricks will be 185s and 186s, and your shells will be 181 and 281 elements. One last note, if you happen to have shared topology between a mixed order mesh, so in my simple example here, I have a block, and that block has attached to it a shell body, and they are sharing common nodes at that interface. Because those nodes are reordered and those bodies are treated separately in the external model utility, that connection of shared nodes will no longer exist when you bring that into mechanical. So you'll have to use a bonded contact region to tie them back together. Okay, so that is the situation where you have a legacy mesh, again, something that came from the MAPDL or classic environment, and you needed to get that into Workbench. Now let's take a different approach. Let's say we may have multiple Workbench users, and what we'd like to do is combine those Workbench models into one single assembly inside Workbench. Now that will be done using the ACT Assembly Manager extension. So just briefly, what is an ACT extension? ACT stands for the Application Customization Toolkit. It is a toolkit that allows users to define custom applications for the Workbench environment. You do need to have an ACS license, that's the Ansys Customization Suite, in order to develop and compile your own mechanical ACT extensions. However, you don't have to have an ACT license to use them. So if someone gives you a binary extension, or if you download one from, say, the Ansys website, there's no licensing required for you to use that. Now, the ACT Assembly Manager is one of two extensions that Ansys has developed that are available with your ACS license, or can be purchased separately from your Ansys support distributor. Another one includes the Component Mode Synthesis extension. Again, either comes with the Customization Suite or can be purchased. Now, the advantage to this ACT Assembly Manager is that you're assembling models with the full details of the source mechanical component. So everything that was used to define that source component is included when you assemble this in the Workbench environment. And those would be things like the material assignment, the geometry, the mesh settings, connections. All of those imported settings, the mesh settings, for instance, can all be edited. They're live. They're not fixed or disabled in any way. So it's almost as if you're taking this model that was created by someone else in another Workbench project and bringing it in as if it was your own inside of your current assembly. Basic procedure: you first install the extension, you generate a mesh for the various components that you intend to assemble. You write out at the component level files that will be used by the assembly manager to basically read that geometry and its mesh into the assembly file. And the assembly manager interface is used to add the components in a couple of different ways. You can do this as patterns. You can do it as multiple assemblies, kind of similar to what we did with the external model utility. So step one, you would build your model separately, and this could be a situation or a scenario where you've got a design team and multiple people are working on different parts of that system. And what you'd like to do at the end of that, after they're done with their individual analyses, is bring those models together as a system model without having to reconstruct or remesh anything. And this is what this assembly extension will allow you to do. So step one is write out the data that's going to be used by the assembly extension from the component. Make sure that your host model contains any of the engineering data that's being used by the imported bodies or models. It's smart enough to recognize those in the engineering data library if they're there, but if you're bringing in a component that has a material that does not exist in the assembly file, it's going to get its default structural steel, and you'll have to correct that. You're going to orient different components in that assembly using coordinate systems. So in your host model, make sure that you've created coordinate systems that you can use for that import. So the example here would be I have the rotor as the base model, and now I want to create coordinate systems that represent the different blade orientations as I bring in multiple copies of the blade. So we access the Assembly Manager extension, and we start to add rows that describe the source folder containing the assembled data and then the target coordinate system that we'd like to use. And the first step in the process is we simply update the geometry in the mesh. And this is a way for you to confirm that everything is positioned and sized accordingly. And then beyond that, we use the update model, which in addition to the geometry of the mesh, also brings over all the additional settings that were used to create that mesh in the original component model. So you'll see these various settings prefixed by the name of the import, the tag name. So we have import underscore edge sizing, import underscore sweep method. These are all the mesh controls that were defined in the original part. And again, these are all live. They can be edited. They can be deleted. They can be changed as needed. Now you can bring in multiple parts. In this case, we brought in multiple blades by referencing different coordinate systems, but there's also an option here to add a pattern, and the pattern consists of a planar or rectangular type of offset, and it works very similar to the pattern capability inside Design Modeler, where you specify the number of copies and the offset, and you do that with one import step. Now the rows in the Assembly Manager, as you can see here, can be made active or inactive, and it simply requires that you update the geometry mesh or update the model to refresh the assembled part. So it's not anything that's fixed in stone. You can remove assembled parts if you need to and bring them back at your leisure. Okay, to view a active recording of the ACT Assembly Manager, we have this on our website at caeai.com on the e-learning page. And as I mentioned before, you can also view a recorded demonstration of this extension on our CAE Associates YouTube channel.